The people attacking your organization are already using machine learning, and so is almost every security product you're asked to trust. Your detection stack, your triage queue, your anomaly alerts. Those are models making decisions, and most defenders can't say how. You can't defend, evaluate, or push back on a system you can't explain. That's why a security channel is teaching AI from the ground up, not as data science, but as the substrate security now runs on. By the end, you'll read an architecture, say what a model can and cannot do, and spot a vendor claim that doesn't hold. We build it in order: neural networks, transformers, large language models, and finally AI agents. Part 1. What is machine learning? Every piece of software you've ever used runs on the same idea. A programmer writes the rules, feeds in data, and the computer spits out answers. Machine learning flips that completely. Instead of writing the rules yourself, you give the computer the data and the answers, and you let it figure out the rules on its own. That shift from hand-coding logic to learning it from examples is the entire reason machine learning exists, and it's why it now powers everything from spam filters to fraud detection to the intrusion detection system sitting on your network right now. So how does a machine actually learn from data? There isn't just one way. There are three major approaches, and each one solves a different kind of problem. Supervised learning learns from examples that already have the right answer attached. Unsupervised learning looks at data with no answers at all and finds structure on its own. And reinforcement learning learns by acting, failing, and getting better through trial and error guided by rewards. Understanding when to reach for each of these is one of the most common things interviewers probe for. So let's break down each one, starting with supervised learning. Supervised learning is the most intuitive of the three because it mirrors how a teacher grades homework. You give the model a big pile of examples, and every single example is already labeled with the correct answer. The model looks at thousands of these input-output pairs and gradually adjusts itself until it can predict the right label for an example it has never seen before. The supervision is literally the labels. A human or a labeled dataset is supervising the learning process the whole way through. Here's a concrete example you already use every day: your email spam filter. It was trained on millions of emails that humans had already labeled as spam or not spam. The model studied the patterns, suspicious links, certain phrases, sender behavior, and learned to associate those patterns with the spam label. Now, when a brand new email lands in your inbox, the model applies what it learned and predicts spam or not spam in a fraction of a second. That's supervised learning in production. Unsupervised learning removes the labels entirely. You just hand the model a pile of raw data and ask it, what structure do you see in here? There's no right answer to check against. The model has to find patterns, similarities, and groupings completely on its own. The most common outcome is clustering. The model naturally groups similar data points together, even though nobody told it what those groups should represent. It's about discovering something you didn't already know was there. This is huge in security. Imagine you feed a model months of ordinary network traffic, logins, file transfers, data volumes, with no labels for normal or attack. The model clusters all of that traffic based on similarity, and over time it learns what normal looks like. So when a login suddenly happens at 3 a.m. from a country your company has never operated in, that data point falls way outside every existing cluster, and the model flags it as an anomaly. Reinforcement learning works completely differently from the other two. There's no labeled dataset and no static pile of data to cluster. Instead, there's an agent that lives inside an environment, and it learns purely through trial and error. The agent takes an action, the environment responds, and the agent receives a reward or a penalty based on how good that action was. Over thousands or millions of these cycles, the agent gradually learns which actions lead to the best long-term reward. Picture an automated incident response system defending a network. When it detects a suspicious process, it can choose an action, isolate the host, kill the process, or do nothing. Each choice leads to a consequence. Correctly stopping a real attack earns a reward, while wrongly shutting down a critical production server earns a heavy penalty. No one hand-coded the correct response for every scenario. The agent discovered it through reward-driven trial and error. So when do you actually reach for each one? If you have historical data with known outcomes, fraud or not fraud, malware or benign, that's a supervised problem. If you have a mountain of raw data and you're hunting for hidden structure or outliers with no predefined labels, that's unsupervised. And if you're dealing with a system that has to make a sequence of decisions over time, learning from consequences rather than a fixed data set, that's reinforcement learning. Let's bring it all together. Machine learning replaces handwritten rules with rules learned from data. Supervised learning learns from labeled examples like a spam filter. Unsupervised learning finds structure in unlabeled data, like clustering network traffic to spot anomalies. And reinforcement learning learns through trial, error, and reward, like an automated response agent defending a network. These three categories show up constantly in security tooling, so knowing exactly which one applies to a given problem is a skill that will serve you well. If this helped clarify the landscape, subscribe. There's a lot more of this coming. Part 2. How neural networks actually work. Last time we saw that machine learning replaces handwritten rules with rules learned from data. But how does a model actually learn those rules? For a huge chunk of modern AI, the answer is a neural network. A neural network is just a stack of simple math units wired together in layers that gradually transforms raw input into a useful output. It sounds abstract, so let's build one piece by piece, starting with how data even gets in. Every neural network starts with an input layer. Raw things like an email, an image, or network traffic don't mean anything to a machine directly, so they first get converted into numbers. A word becomes a number, a pixel's brightness becomes a number, a packet size becomes a number. That list of numbers is what actually flows into the network, each number landing on its own input node ready to be passed forward. This numeric translation step is the same no matter what kind of data you started with. The basic building block of the whole network is the neuron. A neuron takes in several numbers, multiplies each one by its own connection strength, and adds the results together. Think of it as a tiny calculator that combines several signals into one. Every neuron in the network is doing this same simple job, just with different numbers flowing through it. The real intelligence isn't in any one neuron. It's in how millions of these simple sums combine across the whole network. Those connection strengths are called weights. A weight decides how much influence one input has on the neuron's decision. A large weight means that input matters a lot. A small or negative weight means it barely matters or even pushes the result the other way. When a network learns, it isn't learning new rules by hand. It's adjusting these weights, thousands or millions of them, until the combination produces useful answers. Weights are essentially the network's memory of what it has learned. Weights alone aren't quite enough. Each neuron also has a bias, a single extra number added to the weighted sum. The bias shifts how easily a neuron fires, the same way a strict versus a lenient judge might need more or less evidence before ruling. A high bias makes the neuron trigger more easily. A low bias holds it back. Bias gives every neuron a bit of built-in flexibility, so it doesn't just react to inputs, it reacts based on its own adjustable threshold. After the weighted sum and bias are combined, that raw number passes through one more step, the activation function. This function decides the neuron's actual output, often squashing the value into a useful range or blocking it entirely if it's too weak. Activation functions matter because they introduce non-linearity. Without them, stacking layers would be mathematically pointless, just one big straight line. With them, the network can bend and combine signals in ways complex enough to recognize things like a phishing email or a malicious file. A single neuron is limited, so networks group many neurons side by side into a layer. Each neuron in that layer sees the same inputs, but with its own separate weights and bias. So each one learns to notice something slightly different. One might respond strongly to certain patterns, another to completely different ones. Stacked together, a layer turns a handful of raw numbers into a richer set of learned signals, ready to be passed on to whatever comes next. Between the input and the final answer, networks often include one or more hidden layers, so called because we don't directly see their output, only their effect on the final result. Each hidden layer takes the previous layer's output as its new input, combining simple signals into increasingly abstract ones. Early layers might notice edges or basic patterns. Later ones combine those into higher level concepts. Stack enough hidden layers and you get what's called deep learning, a topic we'll dig into fully next time. Eventually, the signal reaches the output layer, the network's final answer. Its shape depends on the task. One neuron might output a single yes or no score, like phishing or not phishing, while others output a probability for each possible category. The output layer takes everything the hidden layers extracted and condenses it into the specific answer the network was built to give. Everything before it exists purely to feed this final decision the best possible information. Now let's trace the whole path at once. Raw data enters as numbers at the input layer. Each neuron in the next layer computes its weighted sum, adds its bias, and applies its activation function. That output becomes the input to the next layer, and the process repeats, layer after layer, until it reaches the output. This single left-to-right journey is called a forward pass, and it's exactly how a trained network turns a new email or file into an instant prediction. So where do the right weights and biases come from? During training, the network makes a prediction, compares it to the correct answer, and measures how wrong it was. That error then flows backward through the network, nudging every weight and bias slightly in the direction that would have reduced the mistake. Repeat this over millions of examples, and the weights gradually settle into values that produce accurate predictions. This is the learning in machine learning, happening one small adjustment at a time. This same layered structure powers a lot of tools security teams rely on. Phishing filters use neural networks trained on millions of emails to catch subtle red flags a rule list would miss. Malware classifiers learn to recognize malicious code patterns even in files they've never seen before. Intrusion detection systems use them to flag network behavior that just looks wrong. Understanding weights, biases, and layers isn't just theory. It's what lets you reason about why these tools sometimes get it wrong too. So, a neural network is layers of simple neurons, each combining weighted inputs, a bias, and an activation function, passing signals forward until they become a final decision. Weights capture importance, bias sets the threshold, and layers stack that logic into something powerful enough to catch phishing, malware, and more. Next time, we go deeper, literally, into deep learning and what happens when you stack many hidden layers together. Subscribe so you don't miss it. Part 3. What is deep learning? Last time we looked at how a neural network works: an input layer, one hidden layer, and an output. That single hidden layer was enough to combine weighted signals into a decision. But real problems, like separating malware from benign files, are messier than one layer can handle. So what happens when we stack many hidden layers instead of just one? Deep learning is simply this: a neural network with many hidden layers stacked between the input and the output, instead of just one. Each layer takes the previous layer's output and transforms it again, passing a refined signal deeper into the network. Stack enough layers and the network learns far more complex patterns than a shallow one ever could. That's literally where the word deep comes from: depth, not intelligence. Here's why depth is powerful. Each layer learns a different level of abstraction. Feed in raw file bytes, and the first hidden layer picks out tiny local patterns. The next layer combines those into structural features, like suspicious code blocks. A deeper layer combines those into full behavioral signatures. By the time the signal reaches the output, the network isn't looking at bytes anymore. It's recognizing malware families. You might ask, why not just make one hidden layer huge instead of stacking many smaller ones? You could try, but a wide, shallow network has to learn every combination of features directly, needing enormous numbers of neurons. A deep network reuses what earlier layers already learned, building complexity gradually, a far more efficient way to represent complicated patterns. Nothing new mathematically inside a deep network. Every neuron in every layer still does the same job we saw last time: multiply inputs by weights, add a bias, pass it through an activation function. Depth just means repeating that simple operation over and over, layer after layer, refining the representation many times before a final decision. Depth sounds great, so why didn't everyone build deep networks from day one? During training, the network sends an error signal backward through the layers to adjust each one's weights. In very deep networks, that signal can shrink so much by the earliest layers that they barely learn at all. This problem is called the vanishing gradient, and for years it made truly deep networks impractical to train. Deep learning became practical once three things lined up: far more labeled data to train on, far more computing power, mostly GPUs, and better activation functions that kept the gradient signal alive across many layers. Around the early 2010s, these pieces came together, and deep networks started dramatically outperforming older approaches, especially on messy real-world data like images, text, and files. So deep learning is a neural network with many hidden layers, each building on the last to learn increasingly abstract representations of the data. That's the engine behind modern malware classifiers, phishing detectors, and facial recognition systems your security tools may already rely on. Whenever you hear deep learning in a product pitch, you now know exactly what's happening under the hood: layers, stacked deep, learning stage by stage. Next time, we'll zoom into one special kind of deep network built specifically for images and visual patterns: the Convolutional Neural Network, or CNN. Subscribe so you don't miss how it works. Part 4. What is a convolutional neural network? Last time, we stacked hidden layers to build a deep neural network. But there's a problem. Feed a full photograph into that kind of network, and every pixel becomes its own input, millions of them. A convolutional neural network, or CNN, is a deep learning architecture built specifically to handle images and visual patterns efficiently. Instead of looking at every pixel independently, it looks for local patterns, edges, shapes, textures, the way your eye scans a picture. In cybersecurity, this is the same technology behind facial recognition access control, deepfake detection, and even turning malware binaries into images to spot visual patterns. Think of an image as a big grid of pixels, each one a number. A small image might have tens of thousands of pixels. A photo could have millions. Connect every pixel to every neuron in a hidden layer, like a regular neural network, and the number of weights explodes into the millions or billions. That's slow to train, easy to overfit, and it ignores something important. Pixels next to each other are related. A pixel is far more useful looked at together with its neighbors, not in isolation. So CNNs solve this by looking at small, local regions of the image at a time, instead of the whole picture at once. This is where the word convolutional comes from. A CNN uses a small grid of numbers called a filter or kernel, maybe just 3 pixels by 3, and it slides across the image, a few pixels at a time. At each position, it multiplies its values against the pixels underneath it and adds up the result. That single number becomes 1 pixel in a new, smaller grid called a feature map, and the filter keeps sliding until it's covered the entire image. Because the same small filter is reused across the whole image, the network needs far fewer weights than a fully connected layer. Different filters detect different things. One might light up wherever it finds a vertical edge, another might respond to horizontal edges, curves, or color transitions. A CNN doesn't use just one filter. It runs dozens over the same image at once, each producing its own feature map, capturing edges, corners, and simple textures. Early in training, the network doesn't know what these filters should look for. It learns the best filter values automatically, the same way it learns weights in a regular neural network, by adjusting them to reduce error. A single convolutional layer only sees simple patterns, so CNNs stack many of them, just like the hidden layers in deep learning. The first layer's feature maps, edges, and textures become the input to a second convolutional layer. That second layer combines them into more complex shapes, like curves and corners. Stack a few more layers and the network starts recognizing whole parts: an eye, a wheel, a padlock icon, a QR code. By the final layers, the network can represent entire objects or patterns, which is exactly why CNNs are so effective at recognizing logos in phishing pages or spotting subtle visual tampering in a screenshot. As feature maps stack up, they also need to shrink, or the network gets slower and heavier with every layer, and that's the job of pooling. A pooling step slides over the feature map and keeps only the strongest signal in each small region, usually the maximum value, discarding the rest, which shrinks its size while keeping the most important information. Pooling also makes the network more tolerant to small shifts, so a logo slightly off-center or a face slightly rotated is still recognized, and convolution and pooling are typically repeated together, layer after layer, gradually turning a large image into a compact set of high-level features. Once the image has been reduced to a small set of high-level feature maps, the CNN flattens them into a single long list of numbers. That list feeds into one or more regular fully connected layers, exactly like the ones from our earlier neural network video. And these layers combine all the detected features to make a final decision. The output might say this is a cat, or in a security context, this login photo matches the registered user, or this file's binary pattern looks like ransomware. A CNN is really two halves: convolutional layers that extract visual features and fully connected layers that make the final call. So that's a convolutional neural network. Filters that scan an image for local patterns. Feature maps stacked into a hierarchy from edges to objects. Pooling that keeps things efficient, and fully connected layers that turn all of it into a final decision. This architecture powers facial recognition on your phone, automated content moderation, and image-based malware detection. But not everything is a static image. What about sequences, a stream of network traffic, or a sentence in a phishing email? Next time, we'll look at recurrent neural networks, the architecture built to handle exactly that. Subscribe so you don't miss it. Part 5. How recurrent neural networks remember. In the last video, we saw how a CNN scans a single image all at once, looking for spatial patterns like edges and shapes. But not all data in security comes as one snapshot. Think about a sequence of login attempts, a stream of firewall logs, or a chain of DNS requests. One event follows another, and the order tells the story. A CNN has no concept of before and after. It just sees a static picture. That's where the recurrent neural network, or RNN, comes in. An RNN reads data one step at a time, and after each step, it carries forward a memory of everything it has seen so far. As log T1 comes in, the RNN processes it and updates its memory. Then log T2 arrives, and the RNN combines it with what it remembers from T1. By the time it reaches T3, it has built up context across the whole sequence. And that context is what lets it flag a threat, like this brute force login pattern that no single log entry could reveal on its own. Why does order matter so much? Picture 4 events on a timeline: a login at 9 o'clock, another at 9:01, a third at 9:02, and then an account lockout. Individually, none of these look alarming. People mistype passwords all the time. But seen in sequence, they form a clear pattern: a brute force attempt hammering an account until it locks out. Shuffle that same set of events into random order, and the pattern disappears entirely, even though the exact same 4 things happened. A model that looks at each event in isolation, or at everything at once with no sense of sequence, will miss this completely. What we need is a system that reads events in the order they occurred and remembers the earlier ones while evaluating the later ones. That sequential memory is exactly the gap an RNN fills, connecting event 1 to event 2 to event 3, until the pattern and the alert it triggers becomes obvious. So what's actually happening inside an RNN cell? At each time step, the cell takes 2 things as input: the new data point, called xt, and its own hidden state from the previous step, its running memory. It combines these, produces an output yt, and an updated hidden state. This self loop is the defining feature of a recurrent network, and it's where the name comes from. The same cell with the same weights recurs step after step, each time folding in a little more history. That hidden state loops back into the very same cell, ready to combine with the next input when it arrives. It's a simple idea, but that one looping arrow is what gives the network memory across an entire sequence, rather than treating each input as if it existed in total isolation. It's easier to see this if we unroll that loop across time. Imagine 3 copies of the same RNN cell laid out side by side, one for T1, one for T2, one for T3. At T1, the cell takes input xt1 and with no prior memory yet produces output yt1 and a fresh hidden state. That hidden state flows sideways into the T2 cell, combining with new input xt2 to produce yt2 and an updated hidden state, which flows into T3 along with xt3. Notice these aren't 3 different networks. They're the exact same cell using the exact same shared weights, just applied repeatedly as time moves forward. That's what makes RNNs efficient. One small set of weights learns a pattern that works whether the sequence is 3 events or 300. The chain of hidden states threading through every cell is the network's growing understanding of everything that came before. This is exactly why RNNs became popular for security use cases involving sequences. Feed a stream of log lines, packet headers, or system calls into an unrolled RNN, and it processes the sequence in order, carrying context forward the whole way through. At the end, the network's final hidden state summarizes everything it just read, and that summary gets passed to a simple classifier that outputs a verdict: normal traffic or an attack in progress. This is the same idea behind intrusion detection systems that flag command and control beaconing, tools that catch slow, low and slow brute force attempts spread over hours, and malware classifiers that examine a sequence of API calls rather than judging a program from a single frozen snapshot. Sequence, not snapshot, is the whole point. RNNs aren't perfect, and it's worth knowing their biggest weakness. As the sequence gets longer, information from early time steps passes through the hidden state again and again, getting rewritten a little each step. By 10 or 100 steps down the line, the signal from that very first event has often faded almost to nothing, often called the vanishing gradient problem. Imagine a sequence that starts with malware dropped to disk at step 1, but the alert doesn't fire until step 10, after several ordinary-looking events in between. A basic RNN may simply have forgotten that critical first clue by the time it needs it most. This short memory span is the main limitation that pushed researchers to look for something better, a way to reach back and reference any earlier moment directly, instead of relying on a fading trail of hidden states. So, to recap, a CNN looks at a whole image at once, but an RNN reads data step by step, sequence data like logs, network traffic, or user behavior, feeding into a recurring cell that carries a hidden state forward as memory, letting it recognize patterns that only emerge over time. Its main weakness is that this memory fades over long sequences. That fading memory problem is exactly what the next building block in the series was invented to solve. In the next video, we'll break down the attention mechanism, the idea that let networks stop relying on a single fading memory and instead look back directly at any earlier point in the sequence. Subscribe so you don't miss it. Part 6. How the attention mechanism fixed AI's memory problem. Last time, we saw the RNN's big weakness. As a sequence gets longer, the signal from an early event like malware drop to disk at step 1 fades almost to nothing by the time an alert fires 10 steps later. That fading memory problem is exactly what today's building block was invented to solve. What if, instead of relying on one compressed memory that degrades over time, the network could reach back and look directly at any earlier moment it needed, no matter how far away? Here's the core idea behind attention. At every step, instead of using just one fading memory, the network keeps around every earlier hidden state it has produced. Then it computes a relevance score between the current step and each of those earlier states, asking, essentially, how much does this past moment matter right now? The thickness of these connections shows that idea. Some past states end up mattering a lot, others barely at all, and the network decides that fresh every single step. Let's make this concrete with a security example. Picture a stream of log events. Step 1 is malware dropped to disk. Steps 2 through 7 are routine, unremarkable activity, until step 8, where a suspicious outbound connection finally triggers an alert. With attention, the model doesn't have to carry that first event forward through steps of a fading hidden state. At step 8, it directly scores all the earlier events and can assign the highest relevance straight back to that original malware drop event, however far back it sits. To make this comparison concrete, attention frames it as a question and label matching problem. The current step forms a query, essentially a summary of what it's looking for right now. Every earlier hidden state carries a key, a short summary of what information that state actually offers. The network compares the query against each key to see how well they match, the same way you'd scan a row of luggage tags to find the one that matches what you're holding. Alongside its key, every earlier hidden state also carries a value, the actual content that gets pulled forward if that state turns out to be relevant. So the key is what gets compared against the query, and the value is what actually flows into the answer once a match is found. In our example, the log entry whose key best matches the current query, the malware drop event, is the one whose value contributes the most to what the model retrieves. Once every earlier state has a raw relevance score, the network needs to turn those scores into something it can actually use for weighting. That's the job of a function called softmax. It takes the raw scores and converts them into a set of weights that are all positive and add up to exactly 100%. The state that scored highest ends up with the largest slice of that weight, but every earlier state still gets at least some small share. Now attention combines everything. It multiplies each earlier state's value by its softmax weight and adds all of those weighted values together into a single new vector called the context vector. Because the weights were driven by relevance, this context vector is naturally dominated by whichever past moments actually mattered, like our malware drop event, while irrelevant steps contribute almost nothing. It's a summary built fresh for this exact moment, not a single memory dragged along the whole way. Here's how this actually plugs into the RNN we already know. At each step, the RNN still keeps its own hidden state, but now it also computes this attention-built context vector by looking back across all earlier steps. The two are combined, and that combination is what actually feeds the prediction. The RNN hasn't disappeared here. It's still processing the sequence step by step. Attention is an add-on that gives it a direct line back to any earlier moment, patching its short memory problem without replacing how it works. So, to recap, attention lets a network score every earlier state's relevance, turn those scores into weights with softmax, and blend the matching values into a fresh context vector, giving it a direct line to any past moment instead of one fading memory. We first bolted this onto an RNN just to patch its weak memory, but researchers soon asked a bigger question. What if you built a whole architecture out of nothing but attention and dropped recurrence altogether? In the next video, we'll break down the transformer, the architecture behind GPT. So make sure you subscribe so you don't miss it. Part 7. How transformers work. Attention gave RNNs a way to look back at any earlier moment, but it left one big problem untouched. An RNN still has to process a sequence one step at a time. Step 2 can't even start until step 1 finishes. On a long sequence or a huge training set, that's painfully slow because it can't be parallelized across time. In 2017, a group of researchers asked a radical question. What if you threw away the recurrence entirely and built an architecture out of nothing but attention? The result was the transformer, and it's the architecture behind every large language model you've used since, including GPT. The core mechanism is called self-attention, and it's the same relevance scoring idea from the last video, just applied differently. Instead of one RNN state looking back through a chain of memory, every single word in the sentence directly attends to every other word, all at once in parallel. Each word asks, which other words in this sentence matter for understanding me? The word it in a sentence can directly attend to the noun it refers to, 3 words earlier or 10 words earlier, with no chain in between and no fading signal. Because every token can see every other token simultaneously, this whole computation happens in one parallel pass instead of a slow step-by-step crawl. But dropping recurrence creates a new problem. An RNN naturally knew word order because it read one word after another. Self-attention looks at all words at once, so on its own it has no idea which word came first, second, or last. It's just a bag of tokens. The fix is called positional encoding. Before anything else happens, the transformer adds a small signal to each word's representation that encodes its position in the sequence. First, second, third, and so on. Now the model can tell the dog bit the man apart from the man bit the dog. Same words, different order, different meaning. A single attention pass only learns one kind of relationship at a time, but language has many kinds at once: grammar, meaning, reference, tone. So the transformer runs several attention calculations in parallel on the same input, each one called a head, and each head is free to learn a different pattern. One head might specialize in tracking which noun a pronoun refers to. Another might track which words modify which other words. All the heads run simultaneously, and their results are combined into one richer representation. This is called multi-head attention, and it's why a transformer can capture far more nuance than a single attention calculation ever could. After the attention step, each token's new representation passes through a small feed-forward network, a simple set of weights and an activation function. The same building block from our neural network video applied independently to every token. 2 more pieces keep this stable across a deep stack. A residual connection carries a copy of the original signal forward and adds it back in, so information from earlier steps never has to survive by squeezing through every single transformation. And a normalization step rescales the values after each stage, keeping numbers in a healthy range so training doesn't blow up or vanish, even dozens of layers deep. Self-attention, multi-head splitting, feed-forward, residuals, and normalization together make up one transformer block. And just like the deep networks we covered earlier in this series, a real transformer doesn't use just one block. It stacks many identical blocks on top of each other, sometimes dozens. Each block takes the previous block's output and refines it further, building progressively richer representations of the text. Early blocks might capture basic grammar, deeper blocks capture meaning, tone, and long-range context. It's the same depth equals abstraction principle from deep learning, just built from attention blocks instead of simple hidden layers. The original transformer from the 2017 paper, Attention is All You Need, was built for machine translation, and it had two halves. An encoder stack reads the entire input sentence at once and builds a rich representation of it, every word attending to every other word freely. A decoder stack then generates the output sentence one word at a time, attending both to the encoder's representation of the input and to the words it has already generated itself. This encoder-decoder split makes sense for translation. Read the whole French sentence, then generate the English sentence. But it's not the only way to use this architecture. GPT, which stands for Generative Pre-trained Transformer, takes a simpler path. It drops the encoder half entirely and uses only a stack of decoder blocks. There's no separate input sentence to encode. GPT just reads whatever text has come so far and predicts the next word, one at a time, using self-attention across everything that's already been generated. Because it's decoder only, GPT's attention is also restricted to look backward only, called causal or masked attention. Each word can attend to every word before it, but never to words that come after, since those haven't been generated yet. That's the entire architectural idea behind GPT, a tall stack of decoder blocks doing causal self-attention over and over. This architecture matters directly for your job. The same transformer that generates fluent text can write a convincing phishing email in seconds, which is exactly why attackers increasingly use it and why the best phishing filters now use transformers of their own to catch the subtle patterns. Security teams use transformer-based models to summarize thousands of log lines or alerts into a plain English incident summary, and to power the AI copilots showing up inside SIEM and EDR tools, answering analyst questions in natural language. Understanding that it's attention, positional encoding, and stacked blocks under the hood helps you reason about what these tools can and can't reliably do. So, to recap, a transformer replaces an RNN's slow, one-step-at-a-time processing with self-attention, letting every token look at every other token in parallel, restores order with positional encoding, captures multiple kinds of relationships with multi-head attention, and stacks many of these blocks deep, just like the deep networks earlier in this series. GPT takes this architecture and keeps only the decoder half, generating text one token at a time with causal self-attention over everything written so far. We now know what the architecture looks like, but how does it actually turn that into the text you see when you chat with it? In the next video, we'll trace how GPT works, from raw tokens all the way to the words on your screen. Subscribe so you don't miss it. Part 8. How GPT works. Last video, we broke down the transformer, the architecture that replaced recurrence with attention. Now let's trace what actually happens inside GPT when you type a sentence and hit enter. The first step is tokenization. Your text gets chopped into small chunks called tokens, which might be whole words, parts of words, or punctuation. GPT doesn't see letters or words the way you do. It only ever sees this list of tokens, each one just an ID number from a fixed vocabulary of tens of thousands of possible pieces. Each token ID is then converted into an embedding, a long list of numbers that captures something about that token's meaning, learned during training. Position information gets added in too, so the model knows not just what each token is, but where it sits in the sequence. Exactly the positional encoding step we covered last video. What comes out of this stage is a stack of number vectors, one per token, ready to be handed to the transformer itself. Those vectors flow up through GPT's stack of decoder blocks, the same self-attention, feed-forward, and residual connection pattern we detailed in the last video, repeated dozens of times. Every layer lets each token refine its understanding by attending to every token before it. By the time the vectors reach the top of the stack, each one carries a rich, context-aware representation, not just of its own token, but of everything that came before it in the sequence. The final layer takes the last token's vector and turns it into one score for every single token in GPT's entire vocabulary, tens of thousands of numbers. A softmax function converts those scores into probabilities that all add up to 100%. In plain terms, GPT isn't looking up an answer. It's computing how likely each possible next token is, given everything it's seen so far in the conversation. GPT then samples one token from that probability distribution to actually output. It usually doesn't just grab the single highest scoring token every time. A setting called temperature controls how much randomness gets mixed in, which is exactly why the same prompt can produce a slightly different answer each time you run it. This is also the root of hallucination. The model is always producing a plausible sounding next token, not consulting a database of verified facts. Here's the part that makes GPT feel like it's writing rather than just answering. That newly sampled token gets appended to the sequence, and the whole thing, your original prompt plus every token generated so far, gets fed back through the entire model again to predict the next one. One token at a time, in a loop, is literally how GPT produces every sentence you've ever seen it write. That loop can't run forever on an unlimited amount of text. Every GPT model has a fixed context window, a maximum number of tokens it can hold and attend to at once. Once a conversation grows past that limit, the oldest tokens fall out of view entirely. The model literally cannot see them anymore, which is why a long chat session can suddenly seem to forget something you said near the start. For security work, this token-by-token, probability-driven process explains a lot. Because GPT always predicts a plausible next token rather than retrieving a verified fact, it can generate convincing text that's simply wrong. And because instructions and untrusted input both just become tokens in the same context window, an attacker can smuggle in text that reshapes what the model does next, the basis of prompt injection. The same fluent text generation also makes GPT-style models a tool attackers use to write phishing emails and scripted social engineering at scale. So that's the full loop. Text becomes tokens, tokens become embedding vectors, those vectors flow through a stack of transformer decoder blocks, the final layer produces a probability distribution over the entire vocabulary. One token gets sampled, appended, and fed back in, again and again, until GPT decides it's done. Understanding this pipeline is what lets you reason clearly about where these models are reliable and where they're not. Subscribe for more AI and ML foundations built for security people. Part 9. Fine-tuning explained. So GPT and models like it start life as a base model, trained once at huge cost on a broad slice of the internet to be generally good at predicting the next token in almost any kind of text. But a business rarely wants generally good. They want a model that reliably follows their support scripts, writes in their house style, or flags their specific category of malicious log entries. Fine-tuning is how you take that expensive general-purpose base model and specialize it without training a new one from scratch. Fine-tuning doesn't need billions of documents. It needs a much smaller, carefully curated set of examples, sometimes just a few hundred to a few thousand, that show the model exactly the input-output behavior you want. A support ticket and the ideal reply, a raw log line and the correct threat label. Quality and consistency matter far more than volume here, because every example is directly shaping how the model's weights shift. Mechanically, fine-tuning is the same gradient descent training loop covered back in the neural network video. Predict, compare to the correct label, compute the error, adjust the weights. The only difference is where you start. Instead of random initial weights, you start from the already trained base model and run a comparatively short additional training run on the small task-specific dataset, nudging those existing weights rather than learning them from zero. Full fine-tuning updates every single weight in the model, which produces strong results but demands a full copy of the model's memory footprint in GPU memory just to train it. That's why parameter-efficient methods like LoRa have become the practical default. They freeze the entire pre-trained model and insert a small set of new trainable weights alongside it, training only that small adapter. You get most of the specialization benefit at a tiny fraction of the compute and storage cost. After fine-tuning, the architecture hasn't changed at all. Still the same decoder-only transformer stack we've covered the last two videos. What's changed is only the numeric values of the weights. Ask the base model and the fine-tuned model the same question, and the base model gives a generic, broadly informed answer, while the fine-tuned model gives one shaped by whatever examples it was tuned on, whether that's your support style, your codebase's conventions, or your security team's alert taxonomy. Fine-tuning too aggressively or on too narrow a dataset has a real failure mode called catastrophic forgetting. The model overrides general capabilities it had before, becoming excellent at the narrow task while getting noticeably worse at everything else. This is one reason parameter-efficient methods are attractive. By freezing the base weights and only training a small adapter, the model's original broad knowledge stays intact underneath the specialization. For security teams, fine-tuning shifts the attack surface onto the training data itself. If an attacker can slip manipulated examples into the fine-tuning set, a technique called data poisoning, the resulting model can be quietly steered to mishandle specific inputs, leak information, or follow hidden instructions, all while performing normally on everything else. Any pipeline that fine-tunes on user-contributed or scraped data needs the same scrutiny you'd give to any other untrusted input source. So fine-tuning takes an already trained base model and continues training it on a small curated dataset, nudging its weights toward a specific task instead of learning from scratch. Done well, it produces a specialized model without the enormous cost of pre-training. Done carelessly, it can forget prior knowledge or absorb poisoned examples. Next video, we'll look at transfer learning, the broader idea that fine-tuning is actually one specific case of. Subscribe for more AI and ML foundations built for security people. Part 10. What is transfer learning? Last video we covered fine-tuning, taking a pre-trained model and continuing training on a small task-specific dataset. That's actually one specific example of a much broader idea called transfer learning, taking knowledge a model learned solving one problem and reusing it to solve a different related problem, instead of learning everything from zero every time. What actually transfers is the model's learned representations, the patterns its earlier layers pick up. A neural network trained on millions of images first learns general-purpose features like edges, textures, and shapes, before its later layers specialize toward the exact classification task it was trained for. Those early general-purpose layers are useful far beyond the original task, which is exactly what transfer learning exploits. The classic transfer learning recipe. Freeze the base layers so that general purpose weights don't change. Remove the original final layer, which was specialized for the old task, and attach a fresh final layer trained from scratch on the new task. Only that new layer, and sometimes a few layers just below it, actually gets trained, which is dramatically cheaper than training the whole network. In practice, transfer learning and fine-tuning sit on a spectrum, not in separate boxes. At one end is training a brand new model from scratch, expensive and data hungry. At the other end is full fine-tuning, updating every weight of a pre-trained model. Classic transfer learning, freezing the base and retraining just the head, sits in between. Less data and compute than fine-tuning, more adaptation than using the base model untouched. This is why transfer learning matters so much in practice. A team with only a few thousand labeled medical images doesn't have to train a vision model from scratch, which could take millions of images to work well. They start from a model already trained on a huge general image dataset and transfer that learned visual knowledge onto their much smaller specialized dataset. Same underlying reasoning that makes fine-tuning practical for language models. Transfer learning isn't free of failure modes. If the source domain and the target domain are too different, a model trained on natural photographs transferred onto satellite radar imagery, for instance, the reused features can actively hurt performance, a problem called negative transfer. The closer the source and target tasks are, the more the transferred representations actually help rather than mislead. For security teams, transfer learning means your model's risk profile isn't fully determined by your own training data. Whatever biases, blind spots, or even a deliberately planted backdoor exist in the source model you built on top of get inherited by everything downstream. Vetting the provenance of a pre-trained base model is now as important as vetting the training data you add on top of it. So transfer learning is the broader principle. Reuse representations a model already learned instead of starting from zero. Whether that means freezing a base and retraining just the head, or fully fine-tuning every weight on a new dataset. It's what makes modern AI development fast and data efficient, and it's why understanding one pre-trained model's history matters for everything built on top of it. Next video, we'll zoom out to look at large language models themselves. What actually makes a model large? Subscribe for more AI and ML foundations built for security people. Part 11. What is a large language model? Last video, we saw transfer learning as the broader idea behind fine-tuning. Now let's zoom out further and answer a simpler question. What actually makes a model large? A large language model, or LLM, is a transformer-based model, the same architecture we covered a few videos back, scaled up dramatically. More layers, more parameters, and trained on far more text than earlier language models ever were. Large really means scaling up along three axes at once: the number of parameters, the learned weights inside the network, the amount of training text now measured in trillions of words, and the compute spent training it, measured in raw GPU hours. Researchers have found fairly predictable scaling laws. Push all three up together, and the model's performance keeps improving in a measurable, roughly consistent way. What makes scale interesting isn't just better text prediction. It's that new abilities show up that smaller models simply don't have. Past certain size thresholds, models start doing multi-step reasoning, basic arithmetic, and following instructions they were never explicitly trained on, just from patterns in enough text. Researchers call these emergent abilities, since they appear fairly abruptly as scale increases rather than improving smoothly. Building an LLM happens in stages we've actually already covered. First, pre-training. The model predicts the next token across a massive scrape of text, learning grammar, facts, and reasoning patterns purely from that objective. Then comes fine-tuning and alignment, using the techniques from a couple videos ago to shape that raw base model into something that follows instructions and responds the way a helpful assistant should. Scale doesn't fix everything. LLMs still hallucinate, generating fluent, confident sounding answers that are simply wrong, because the model is predicting plausible text, not looking anything up. They also only know what was in their training data, so anything that happened after their training cutoff is invisible to them unless it's fed in some other way, which is exactly the problem later videos on retrieval will address. LLMs also split along how they're distributed. Open-weight models publish their trained parameters, so anyone can download and run them locally, inspect them, or fine-tune them further. Closed models keep their weights private and are only reachable through an API, which matters a lot for security teams. With an open-weight model, you can audit exactly what you're running. With a closed one, you're trusting a vendor's infrastructure and their guarantees about your data. For security teams, an LLM is a new kind of attack surface. Any text fed into the model, a document, a web page, an email, is effectively untrusted input, and attackers have learned to hide instructions inside that text to hijack the model's behavior, a technique called prompt injection. Understanding what an LLM actually is, a next token predictor trained on data, not a reasoning oracle, is the first step to reasoning clearly about where it can be manipulated. So an LLM is just a transformer scaled up along parameters, data, and compute until new abilities emerge that smaller models don't have, then aligned through fine-tuning to behave like a helpful assistant. But everything an LLM generates comes from patterns in its training data and the text in its current context window, nothing more. Next video, we'll look at how models actually represent meaning internally through embeddings, turning words into numbers a network can reason over. Subscribe for more AI and ML foundations built for security people. Part 12. Why every AI model turns text into vectors first. Last video we ended on a question. How does a language model actually represent meaning internally? The answer is embeddings. An embedding is a list of numbers, a vector that represents a piece of text, a word, a sentence, even a whole document. Instead of storing cat as the letters CAT, a model stores it as something like a string of a few hundred decimal numbers. The key idea is that these number lists aren't random, they encode meaning through position. Words used in similar contexts end up as vectors that sit close together in this numerical space. Dog and puppy land near each other, while dog and spreadsheet land far apart. Distance in this space becomes a measurable stand-in for how related two pieces of text actually are. The flat map we just pictured is only 2 dimensions for the sake of explanation. Real embeddings usually have anywhere from a few hundred to a few thousand dimensions. Each dimension captures some learned feature of meaning, though not features humans would name individually, and together they let the model place text with far more precision than any 2D or 3D picture could show. Nobody handwrites these number lists. A network learns them during training by repeatedly predicting words from their surrounding context. The same next token objective from pre-training we covered a few videos back. Words that keep showing up in similar contexts get pushed towards similar vectors, purely as a side effect of getting better at that prediction task. Embeddings aren't limited to single words. Whole sentences, paragraphs, entire documents, and even images can each be turned into a single vector that represents their overall meaning or content. That's what makes embedding so useful as a general purpose tool. Almost anything can be converted into a comparable numerical form. To actually compare two embeddings, you calculate a similarity score between their vectors, most commonly cosine similarity, which measures the angle between them rather than raw distance. A high score means the two pieces of text are semantically close. A low score means they're unrelated. This single number is what powers semantic search, recommendation systems, and, as we'll see next video, retrieval for language models. Security teams already use embeddings in practice. Turning logs, alerts, or malware samples into vectors lets you semantically search for similar past incidents, even when the exact wording differs. But it cuts both ways. Embeddings built from sensitive documents can sometimes be partially reversed to leak information about the original text. So treat an embedding store the same way you treat the data it was built from, not as some safely anonymized byproduct. So an embedding is just a learned list of numbers that captures meaning, close together for related text, far apart for unrelated text, across hundreds of dimensions we can't fully visualize. But knowing how to create embeddings is only half the story. Next video, we'll look at where all these vectors actually live once you've generated millions of them, vector databases. Subscribe for more AI and ML foundations built for security people. Part 13. What is a vector database? Last video, we ended with a question. Once you've turned millions of pieces of text into embedding vectors, where do they actually live? A regular database built for exact matches and simple filters isn't built to answer, find me the vectors closest to this one across millions of entries fast. That's exactly the problem a vector database is built to solve. Checking a query vector against every single stored vector one by one would work, but it gets painfully slow at scale. So vector databases use approximate nearest neighbor search, ANN for short, algorithms that quickly narrow down to a very lightly set of close matches without comparing against everything. You trade a small amount of accuracy for a massive gain in speed, and for most real use cases, that trade is well worth it. To make that fast lookup possible, a vector database builds an index, an internal structure, often a graph or tree, that organizes vectors so nearby ones are easy to reach without scanning everything. Building this index takes real work upfront, but it's what turns a similarity search across millions of vectors into something that returns in milliseconds instead of seconds. A vector on its own is just a list of numbers, so a vector database stores each one alongside a reference back to its original content, the source text, a document ID, timestamps, permissions, whatever metadata matters. When a search returns a matching vector, that link is what lets you actually retrieve the real content it represents. End to end, a query looks like this. Your search text gets converted into an embedding using the same model that built the stored vectors. That query vector gets compared against the index inside the vector database, and the closest matches come back, each one pointing to its original piece of content. Same embedding step from last video, just running at query time instead of storage time. In practice, you'll run into two flavors of this. Purpose-built vector databases are designed from the ground up around this kind of search. But plenty of existing databases, relational and document stores alike, now bolt on vector search as an added feature. Both approaches work. The right choice usually comes down to how much of your data was already living in one system versus the other. A vector database is still a database. If it holds embeddings of sensitive documents, it needs the same access controls you'd put on the source data, since those embeddings can still leak information. There's also a newer risk, data poisoning. If an attacker can insert crafted content into the database that later gets retrieved by an LLM, they can influence what that model sees and responds with. A risk we'll dig into more once we cover retrieval directly. So a vector database is just a specialized store built to index embeddings and quickly find the closest matches at scale, returning a link back to the original content each time. We now have every piece we need: an LLM that generates text, embeddings that represent meaning, and a database that can retrieve relevant content fast. Next video, we'll put all three together into RAG, Retrieval Augmented Generation. Subscribe for more AI and ML foundations built for security people. Part 14. RAG Explained. We now have every piece we need: an LLM that generates text, embeddings that represent meaning, and a database that can retrieve relevant content fast. But there's a gap. An LLM only knows what was in its training data, frozen at some point in the past. It has never seen your company's internal documents, this morning's incident report, or your private code base. Ask it about any of that, and it either says it doesn't know, or worse, it confidently makes something up. Retrieval Augmented Generation, RAG, solves this by combining two steps instead of relying on the model alone. First, retrieval. Given a question, search a knowledge base for the documents most relevant to it. Second, generation. Hand those retrieved documents to the LLM along with the question and let it generate an answer grounded in that specific content. The model isn't guessing from memory anymore, it's reading before it answers. Here's the full pipeline. The user's question gets converted into an embedding, just like we covered 2 videos ago. That embedding is used to search the vector database for the closest matching content. The matching documents come back, and now we have the raw material for an answer. Those retrieved documents get stitched together with the original question into a single prompt, and that whole package goes into the LLM's context window. The model then generates its answer the same way it always does, by predicting the next token. But now, those tokens are grounded in actual retrieved text instead of just whatever the model happened to memorize during training. You might ask, why not just retrain the model on the new data instead? Because retraining a large model is slow and expensive, often taking days and significant compute. Updating a vector database, by contrast, is as simple as embedding a new document and inserting it. RAG lets you keep the model's knowledge current without ever touching the model itself. RAG isn't magic though. If the documents in your vector database are outdated, wrong, or poorly written, the model will confidently generate answers grounded in bad information. And RAG doesn't fix the model's underlying reasoning limits either. It just gives it better material to reason with. Garbage in the retrieval step still means garbage in the answer. This creates a new attack surface. If an attacker can slip a document into whatever gets indexed into your vector database, whether that's a support ticket, a wiki page, or a scraped web page, they can plant instructions that the LLM will treat as trusted context and follow. This is called indirect prompt injection through RAG, and it's one of the more serious emerging risks in deployed AI systems. So RAG is retrieval plus generation. Search a vector database for relevant content, then hand that content to an LLM to generate a grounded answer. It keeps models current without retraining, but it inherits the risks of whatever gets indexed. Next video, we'll look at AI agents, systems that don't just answer questions, but take actions on their own. Subscribe for more AI and ML foundations built for security people. Part 15. AI Agents Explained. So RAG is retrieval plus generation, and it inherits the risks of whatever gets indexed. Everything we've covered so far describes a system that answers questions. You ask, it responds, the interaction ends. An AI agent is different. It's an LLM wired up to take actions, not just generate text, and to keep working toward a goal across multiple steps without a human in the loop at every step. Most agents run on a simple loop. First, reason. Given the goal and everything observed so far, decide what to do next. Second, act. Actually carry out that step, like calling an API, running a query, or writing a file. Third, observe. Look at the result of that action. Then, loop back to reasoning with that new information and repeat until the goal is done. By itself, an LLM can only generate text. What makes it an agent is giving it tools, defined functions it can choose to call, like searching the web, running code, querying a database, or sending an email. The model decides which tool to use and with what input. The tool executes outside the model, and the result gets fed back into the model's context for the next reasoning step. This is what separates an agent from a single prompt response call. Give it a goal like find and summarize this week's critical CVEs, and it can break that down into steps. Search for advisories, filter by severity, pull details on each one, and compose a summary, all without a human approving each individual step along the way. In practice, complex agent systems often split work across multiple specialized agents coordinated by an orchestrator. One agent handles research, another writes code, another reviews it, and a top-level controller manages the handoffs between them. This mirrors how a human team divides labor, except each specialist is an LLM configured with its own tools and instructions. Giving a model the ability to act, not just talk, raises the stakes considerably. A hallucinated fact in a chat response is embarrassing. A hallucinated decision that triggers a real API call, a real file deletion, or a real financial transaction is a genuine incident. The more autonomy and tool access an agent has, the more damage a single bad reasoning step can cause. This is where prompt injection becomes especially dangerous. If an agent reads a web page, an email, or a document as part of its task, and that content contains hidden instructions, the agent may follow them because it can't reliably tell your instructions apart from instructions embedded in data it's processing. Combined with tool access, that's an attacker directing real actions through your own agent. So an AI agent is an LLM wired up with tools, running a reason act observe loop to pursue a goal across multiple steps with minimal supervision. That autonomy is powerful, and it's exactly why prompt injection and tool misuse are such serious risks in agentic systems. Next video, we'll step back and look at foundation models, the large general-purpose models that everything we've covered gets built on top of. Subscribe for more AI and ML foundations built for security people. Part 16. The base model behind every modern AI. Last video, we covered AI agents, LLMs wired up with tools to reason, act, and observe. But that raises a question. Where does the underlying model itself come from? Most of the systems we've discussed in this series, chatbots, fine-tuned classifiers, RAG pipelines, agents, are all built on top of the same kind of starting point, a foundation model. A foundation model is trained once at massive scale on broad and diverse data, text, code, sometimes images or audio, without being aimed at any single task. That single expensive training run produces a general purpose model that captures broad patterns in language, reasoning, and knowledge, rather than being built to do one narrow job. This is the relationship we described back when we covered fine-tuning. The foundation model is the shared starting point, and fine-tuning adapts a copy of it to a specific domain, medical text, legal text, customer support, without retraining from scratch. The foundation model itself usually isn't specialized for any of those. The specialization happens downstream. That's where the name comes from. A foundation model is the base layer that everything else in this series gets built on top of. Chatbots, RAG pipelines, fine-tuned classifiers, and agents are all applications sitting on top of a shared foundation rather than separate models built from the ground up. Part of what makes foundation models distinct is scale. As model size and training data grow large enough, capabilities that weren't explicitly trained for, basic arithmetic, following multi-step instructions, limited code generation, start to show up. Researchers call these emergent capabilities, and they are a big reason foundation models generalize so far beyond their original training objective. That shared foundation structure cuts both ways. A bias, a training data flaw, or a vulnerability in a widely used foundation model doesn't stay contained. It propagates into every chatbot, every fine-tuned variant, and every agent built on top of it. One upstream weakness becomes many downstream weaknesses simultaneously. This is why foundation models are a supply chain security concern, not just a machine learning one. Most organizations don't train their own foundation model, they build on top of one from a handful of providers. That means a compromised, poisoned, or backdoored foundation model can affect every downstream product built on it across many organizations at once. So a foundation model is a large general-purpose model trained once on broad data that chatbots, fine-tuned variants, RAG pipelines, and agents all get built on top of, which also makes it a single point of failure worth taking seriously. Next video, we'll wrap up the series by looking at model parameters, what it actually means when a model is described as 7B, 13B, or 70B. Subscribe for more AI and ML foundations built for security people. Part 17. What are model parameters? Last video, we wrapped up our look at foundation models by mentioning that models get described with numbers like 7B, 13B, or 70B. So what does that actually mean? That number is the parameter count, the number of individual values inside the model that were learned during training. 7B means 7 billion parameters. It is the single most common way the AI industry sizes and compares models, so understanding it is essential. Each parameter is a numeric weight attached to a connection inside the model's neural network. Before training, these weights start out essentially random. During training, the model sees huge amounts of data, makes predictions, checks how wrong it was, and nudges every single weight slightly to reduce that error. Repeat that process billions of times across billions of weights and you get a trained model. So when someone says a model has 7 billion parameters, they mean 7 billion of these individually tuned dials. Roughly speaking, more parameters means more capacity to capture patterns, nuance, and knowledge. A small model with a few billion parameters can still be genuinely useful, but a much larger model can hold more of the subtlety in language, reasoning, and specialized knowledge. That is why the industry keeps pushing parameter counts higher, and why the same base architecture gets released in multiple sizes, like a 7B version and a 70B version of the same model family. Bigger is not free. Every parameter has to be stored in memory and processed every time the model runs. A 70B model needs far more GPU memory and far more compute than a 7B model, which directly translates into higher hosting costs and slower response times. This is why organizations do not always reach for the largest model available. They weigh capability against the real cost of memory, compute, and latency for their specific use case. One way teams manage that cost is quantization. It does not change the number of parameters, it changes how precisely each one is stored. Instead of storing a weight as a high precision number, quantization rounds it to a lower precision format, which shrinks memory use and speeds up inference, usually with only a small hit to accuracy. This is how a 70B model can sometimes run on a single consumer GPU. Same parameter count, lower precision per parameter. Parameter count is a useful signal, but it is not the whole story. A model with more parameters trained on poor quality data or trained badly can be outperformed by a smaller model trained carefully on better data. Architecture, training data quality, and fine-tuning all matter alongside raw size. So when you see a parameter count, treat it as one data point about capacity, not a guarantee of quality. For security people, parameters matter beyond performance. Those billions of learned weights represent enormous investment, and they are the actual intellectual property of an AI system. That makes them a target. Model theft, where attackers exfiltrate the raw weight files, and model extraction attacks, where attackers query a model repeatedly to reconstruct a copy of its behavior. Both aim at stealing those parameters. Protecting a deployed model means protecting its weights, not just its API. That closes out this series. We started with attention and transformers, moved through GPT, fine-tuning and transfer learning, covered embeddings, vector databases and RAG, looked at AI agents and foundation models, and now finished with parameters. What they are, why they cost what they cost, and why they matter to security. None of this replaces deep technical study, but you now have the vocabulary and mental models to ask sharper questions about any AI system you are asked to secure. Thanks for watching this whole series, and subscribe for more AI and ML foundations built for security people.